vector bundles. So we have seen this in Vamsi's talk, so it will be kind of a repetition with hopefully some examples added in. So I take a manifold M and I define a vector bundle on it. So a vector bundle is a smooth manifold. So a vector bundle of rank n is a smooth manifold itself. And a projection. So this is a definition I'm hoping many of you have seen before, and definitely if you're paying attention also in Vamsi's lecture. Such that, so the fibers of this map are vector spaces. Okay, so each fiber by inverse M, which we call Em for any point in M, is a vector space. And we have a local triviality condition which means that in small neighborhoods of this manifold, this is just a product. So that is, for any point in M, there exists a neighborhood containing that point, such that the part of the vector bundle above that open set, which we also denote by E restricted to U, there is a so I should say there exists a neighborhood and a diffeomorphism. And this is a very special diffeomorphism. It respects the vector space structure on the fibers. Okay, so what that means is that if you look at this E restricted to U, on the first component it's the identity, and on the second component it will be a vector space isomorphism. So that means that when you restrict phi U to a point, let me just call it M, this is a map for a fiber of E to M times Rn, sorry, rank n is Rn, is a vector space isomorphism. So, is this new to anyone here? You've all seen this before. Okay. So what are some examples of a vector bundle? Huh? The tangent bundle. That's a very complicated example. What is the simplest example? Huh? The trivial bundle. Okay. So the trivial bundle is an example. So what's the simplest non-trivial bundle you can think of? The least rank?
Mobius.
Yes, the Mobius strip. So take n to be S1 and the rank of the vector bundle is 1. And since we want a non-trivial bundle, it's a Mobius strip. And of course, there's tangent bundle. So you see that what's going on in the Mobius strip is that didn't come prepared to draw a Mobius strip. So locally it looks like a strip. So it's a rectangle. So in small segments you have it's a interval times r. But when you go around, so when you say r, there is a point which is 1, right? So if you keep following this point 1 and you go around the circle, you will end up at a different point. So globally you cannot have a trivialization, right? So the third example, as someone said, is tangent bundles. So let's maybe focus on the tangent bundle of a sphere. So so if you take a small neighborhood of the sphere and you straighten it out, then you can see all the tangent spaces can be identified to R2, right? So since you have flattened it out and made it sit inside R2, any tangent space you can also be thought of as just being R2. So that gives a local trivialization. So in particular, what I can say is that I can say that this is my x coordinate, this is my y coordinate. You can take another point. I can say this is my x and this is y. But if I want to go around trying to assign coordinates like that, I won't be able to do it, right? So I cannot assign x, y coordinates globally. So another definition of vector bundles is, any questions about this? So another definition of vector bundle, which we also saw in Ramsey's talk, is via transition functions. So let's see what those are. So we have, for different open sets, we have different local trivializations. So transition functions keep track of how these different transition functions patch up. So if you look at the intersection of two open sets, let me call these open sets U alpha and U beta. So U alpha and U beta are open sets in the base manifold. So we have local trivializations. And this is phi alpha and this is phi beta. So these are these maps U which I wrote earlier. And both of these are isomorphisms. So if we compose, so this is a kind of transition function. And what is it? So it has two components. It has to give me a value in the base manifold and something in Rn. So what is the first component going to be? Yeah, it's just the identity U. And the second coordinate, let's see. So let me just write it this way out right now. Analyze it separately. So you take a point in U, and then this map sends Rn to Rn, right? And remember, we said that fiber-wise, this is a linear vector space isomorphism, which means that this guy is a vector space isomorphism, which means that this whole thing can be thought of as an element in GLNR. So more concisely, these transition functions can be expressed as maps to GL and R, right? And they satisfy a co-cycle condition, which means they satisfy co-cycle, which says three things. If you were to use the same chart, you get identity. That's obvious. So this is literally doing this and its inverse. So that's also going to give you identity. And the third thing is, if you have three of these, if you have a triple intersection, then going from alpha to beta, beta to gamma, and gamma to alpha should bring you back to the same thing, which is written like beta alpha, beta alpha gamma is identity on triple intersection. So an exercise in Vamsi's talk was, if you have this, you can go there. Or conversely, you can also do the converse exercise. Like given a, so if you have one piece of information, you can derive the other piece of information. And what exactly do I mean that, so if you are, so the other definition of vector bundle was alternate definition of vector bundle consists, so a vector bundle literally consists of bunch of a cover. So let's say this belongs to a family A, and transition functions for every intersection, which is defined on intersection contains maps in GL and R and satisfies co-cycle condition. So this is a vector bundle. And what vector bundle is it? Like that we don't see a total space. So E is the total space of the vector bundle. So in this definition, the total space is not apparent. So how do you describe the total space? Can anyone recall? Huh? Okay, sorry. Yes, take a disjoint union. Alpha cross Rn. There is an equivalence relation which you get using these transition functions. And let's write it. So this is something in U alpha cross Rn. It will be equivalent to something in U beta cross Rn exactly when these two are the same points in M. And is it visible? So X and Y are the same points in M, and V and W are related via these transition functions, which means that W is Is that okay? Questions? So it will be a good exercise to take some of these vector bundles here and try writing down the transition functions. So even for S2, you can try writing the transition function of the tangent bundle. So another thing you've already seen is section of a vector bundle. So that is, the section of a vector bundle is a smooth map such that it satisfies this condition. So another way of saying this is that any point of M is mapped to a fiber over that point. So it's like you're taking a vector bundle and cutting it open, and not at a zero section, well, possibly not at a zero section, but at some other place. So it's like, it's a kind of a cross section of the vector bundle. So that's why it's called a section. And we denote by this symbol, capital gamma of M comma E, as the space of smooth sections on E. So all maps are smooth, so I am not writing down smooth anywhere. Okay. So we'll see examples of sections in some time after I define a few more things. So what we have been encountering earlier, and we'll in Vamsi's talk, and we'll see more of this in my lectures, is vector bundles with additional structure. So one is E comes with a fiber-wise positive definite metric. Positive definite metric. So what another way of writing this is for every fiber of E, you have a positive definite metric that varies smoothly with X. Okay. Have you seen this structure before? Where? A Riemannian metric. Yeah. So if E were the tangent bundle of a manifold, then this kind of a thing will be called a Riemannian metric. Okay, so if you have a bundle with a positive definite metric, then we can choose trivializations which respect these structures. So you take the standard standard inner product on Rn, and you can demand that your local trivializations respect or are fiber-wise isometries. So we can choose trivializations to be fiber-wise isometries. Okay, so that then once you do that, what can you say about the transition functions then? So if you look at the transition function at any point in the intersection, it's a map from Rn to Rn, but additionally it will preserve this metric. So it is not just an element in GL and R, it is an element in which group? Yeah. So the transition functions will land in O and R. So transition functions are maps from intersection of opens in a manifold to O and R.
How do we choose so that they are fiber-wise isometric? How do we choose trivialization so that it's fiber-wise isometric? To Rn and standard?
Maybe we take any frame and apply Gramsci.
Does that help? Let's think about it.
Orthonomic times they are relating to ortho.
Yeah, basically you can, the thing to keep in mind is that if you have any trivialization, you can change the trivialization linearly, and these coefficients are functions on U. So when you do when he says a Gram-Schmidt or orthogonalization, you can do it in a family. So your coefficients won't just be numbers, but they'll be functions in U alpha. So yeah, I think this is makes sense. And any other questions? Okay. So things which are labeled exercises, do try to work those things out, especially if you are new to the material. And if you have trouble, you can ask me. Okay, so that is one possible structure we can put on a vector bundle. So there's other structures that we have been seeing the last 2 days. So one is a complex vector bundle. So similarly, I will. So complex vector bundle means that every fiber is a complex vector space. And similarly what we did there, so let's actually write down this point. Every fiber is a complex vector space. So we have charts of the following form. So how do you, so if you have a real vector bundle, how can you put additional structure on it so that it becomes a complex vector bundle? Like here we took a real vector bundle and we took the additional data from metric. So whereas complex vector bundle, that just seems like a different different creature. Is it just a matter of putting some more structure on it?
And put a complex structure like a fiber-wise.
Yes, exactly. So you can, you need to know how to multiply by I, and that multiplication by I is an R linear map. So complex structure means that you have an R linear isomorphism which satisfies this condition and varies smoothly with X. Then that will make a real vector bundle into a complex vector bundle. Okay. So if you have a complex vector bundle, you can write charts like this, and your transition functions are going to be from intersections. So note that 2m is m. Sorry, let me make this m. And since we are dealing with rank n vector bundles, 2m is n. So where are the transition functions going to land in? So the transition functions are going to be complex linear. So therefore they land in GLMC. And so on. You can put many such structures. You can take a complex vector bundle and put a Hermitian metric on it. Then your structure group. This group is called a structure group. This group that would be UN. And you can take, say, if you have a metric, and in addition you assign each of your fibers has an orientation. So then your structure group will be SON and so on. So let's do an example of a complex vector bundle which we have already seen before. So let me CP1. So let's define rank 1 complex vector bundle. So we have two definitions of vector bundles, but the first one is very hard to define anything. So if you want to specify a vector bundle, in the second definition you just need to give transition functions. So I'm going to use that definition. So I split up my CP1 into two charts. So you can see. So this consists of, this is just missing one point, that is when the first coordinate becomes 0, and this is missing one point where the second coordinate becomes 0. So together they cover the whole manifold, right? And so these are the affine opens. So let's call this U alpha and U beta. So in order to specify your vector bundle, all you need is a single transition function which goes from the intersection. The intersection is C. What is the intersection?
Both of them.
Huh?
Both of them.
Sorry, I can't hear you.
Both non-zero.
Yes, so what is that?
One.
Yes, C star. So it is C with 0 taken out, because from here you will just miss one point. So C with the 0 taken out, and it maps to GL1C, which is what? C star. So you literally have to specify a map from C star to itself, and that's going to give you the bundle. And what are, can you classify this map topologically? Like topologically, what are the possible maps you can have? Okay, just give me an example of a map. Huh? Sorry.
1 by 0.
Yeah, 1 by 0, why not?
Z.
Z. So, huh? Exactly, Z to the n. So you can just take any n there. So if you look at it, both of these deformation retract to S1. So it's literally a map. At a topological level, it's just a map from S1 to S1. So the degree of the map classifies it topologically. So and so that is just classified by this integer n. Okay. So this. So in fact, let me take z to the minus n because of how I have taken the charts and all. If I take z to the minus n, the resulting bundle is something you've been seeing. Any guesses? Anybody? This you have to know in advance. Yes. Okay. So this is the way to write down the transition functions for these bundles On, and you also see that the complex vector bundles, the complex line bundles over CP1 are just kind of topologically characterized by this one number, and this turns out to be the first Chern number. So in general, if you have a Riemann surface, the line bundles are the complex line bundles are classified by the first Chern number, because you can take out a small disk and in the rest of the outside of the disk, the bundle can be trivialized. And when you add a disk, you have this kind of a situation, and the degree of the transition function is going to be your first Chern number. Okay, and one other thing I want to point out before we move on is the difference between a complex vector bundle and a holomorphic vector bundle. So, a complex vector bundle just has complex vector spaces as fibers, whereas a holomorphic vector bundle requires that these maps are holomorphic. Okay, so holomorphic vector bundle is a complex vector bundle with holomorphic transition functions. And we can see using our you remember we defined our bundle as this disjoint union, right? So when we are in the complex case, this would be Cn. So this is a complex manifold, and you are modding out by a relation which is holomorphic. So as a result, if these transition functions are holomorphic, the resulting E, then in this case E is a complex manifold. Whereas that need not always be the case for complex vector bundles. If you take any random transition functions, the total space is not going to be a complex manifold. Any questions?
What is the first Chern number?
What is the first Chern number? I'm not defined it. I'm assuming you already know it. Yeah, I'm not attempting to define it here. If you have already seen it, this is what it is.
If you take a connection, calculate its curvature, and you integrate it over the manifold, the answer does not depend on what connection you choose. and it's going to be an integer always, and it'll be the first chunk number, whatever she has written.
2 pi I can.
Well,
Yeah.
2 pi I modular normalization. Yeah.
So, and one example of sections which I'm tempted to do, because that's one of the only examples which can be done easily. So since Vamsi didn't do it, I'm going to take the opportunity to do it. So this is seriously an aside. So what are the holomorphic sections? On ON. So before we do this, let me ask you, what are the smooth sections of any given vector bundle? Like if you are given a vector bundle, can you, are there always smooth sections, or are there vector bundles which do not have smooth sections? Right?
You can cut off by
Exactly. So this is, because you can just take one of these charts with the local trivialization, and you take a bump function on it, and outside of it, you say your section is 0. So you have produced a smooth non-zero section. But that section, whereas holomorphic sections are far more restrictive. And so now that I know that ON is a holomorphic vector bundle, a holomorphic section is one which is holomorphic, treating both of these as complex manifolds. Right? If you just have a complex vector bundle, this concept doesn't make sense. But since you have both of these as complex manifolds, you can ask what are the holomorphic sections. So, what's the answer for this from your earlier, from the morning?
degree n
Sorry.
degree n homogeneous polynomials. So that would be like x to the n because it's dimensional.
Right. So exactly. So you have the answer. So I'll just try to write it down using our description of that vector bundle, of a complex vector bundle. So if sigma is a section, on U alpha, you can think of it as a holomorphic function from P1 to C, and it's going to be of the form right? Because it's an entire function, sorry.
There is only one. If P1 is one dimensional.
Sorry, P1 is one dimensional, yes.
Z, why are we writing Z, right?
That is powered.
I'm just doing a Taylor series expansion. So we have a holomorphic function defined on all of C. So I just do a Taylor expansion. Okay. So when I say on U alpha, I mean the trivialization of U alpha. So now let me move to U beta trivialization. So when you go from U alpha to U beta, you need to multiply by z to the minus n. So the same section, when you write it in the other trivialization, it becomes and remember that on U beta we had a different coordinate w, which is related to z as w is 1 by z, right? So when you do this change, this thing becomes, let me just write it out now. A0 will be w to the n, A1 is w n minus 1, so on. An is constant. So if sigma were a holomorphic section, this is something which should be an entire function on C. Right? On U beta, that is. So right? So then what is the condition on the AIs? Right. So all these should drop out. So AI is 0 for I greater than equal to N plus 1. So we got back the result which Abhishek first said is that the sections of holomorphic sections of this vector bundle are exactly the degree n polynomials. So, and it has non-zero holomorphic sections only when n is non-negative. If n is negative, then we don't have anything. We only have the zero section. Okay, now we've seen some of vector bundles. Now we come to kind of closer to the topic of these lectures, which is how to differentiate sections on a vector bundle. So suppose if you're just on a trivial bundle, then if I have a section, can you differentiate it at any point? Like if I take a vector B, can we differentiate it along B at sigma? In an intuitive way, like don't think too much. How would you do it? If you're say just out of class 12.
Directional derivative.
Huh?
Directional derivative.
Exactly, just do directional derivative. But then what happens in a general vector bundle is that the fibers are not canonically identified to each other. Here we are kind of assuming that, so if this is your U and these are your various copies of Rn, we are assuming that all these copies are the same. Okay, so we can identify all to each other and just think of sigma as a map to Rn rather than a map to a vector bundle. So that's the simplification we are making in this simplified version of things. But in a general vector bundle, if you have on a vector bundle, if you have two close nearby points, there is no canonical identification between the fibers. No canonical identification. Of course, they both have a linear structure, so you can take any linear map, but there are like tons of options. So there's no one way to kind of paste together these two. So then, if my section is going like this, maybe these two are the same points, maybe these two are the different points, I don't know, so I can't differentiate. So, so in order to differentiate, I need to make a choice of an object which is called a covariant derivative. So let me say what that is. covariant derivative is a map which takes in a section of E and a vector bundle, a vector field on M, and outputs a section of E. So just in case, by this I mean vector fields on M. Alternately, in this, if you want to stick to the same notation, it is a section on Tm. Okay. And I'm not doing anything. I'm just literally saying that this is my derivative. Like, feels like cheating at this point, but I'll justify it. So if I have a sigma, which is a section, and if I have a vector at a point on the tangent space, you literally say that this is my directional derivative given by this map. Okay, but it has to satisfy certain properties. So let me say covariant derivative is that satisfying. The first property is that it is tensorial in. So the word tensorial just means that if you or C infinity M means real valued functions on the manifold. So if you multiply a function here, it just comes out of the output like that. Okay. So that's the meaning of tensorial. But it is not tensorial on sigma. It satisfies a different kind of rule, which is the Leibniz rule, which is if you multiply a function to sigma, this is section, the types are okay. So you get an additional term. You don't just get this, you get an additional term. So let's make a few remarks. Okay, so it's not in the second on the section variable on sigma, it is not C infinity M linear, but is it R linear? How do you see that?
Because that is VF.
Yes. So if you just take f to be a constant function, then df is 0. So is R linear? It's sigma. That's not an issue. Then my was okay. So my next remark is about what this tensorial means. So tensorial means that if you want to evaluate this thing at a point, then the extension of V doesn't matter. So if you know your section and you know your vector field at one point, you can find the value of this at that point. Okay? So to know sigma p at a point, say M, it's enough to know V M, not all of V. You don't even need V in a neighborhood. And that's something you can convince yourself pretty easily using this rule, because if you take two different v's which have the same value at a point, they differ. So one will be f multiplied the other, right? And since we have this linearity in f, it doesn't matter what your extension of v is. Whereas that is not the case with sigma, because you don't want it to be the case with sigma, because you are differentiating sigma. So then you shouldn't just depend on the value of sigma at one point, it should depend on the value of sigma in the neighborhood. And my third remark was, yeah, and because it is tensorial, you can, if you did not know this vector field and you just plug in a sigma, then it's kind of a linear function on the vector field. So you can think of this as an element in. So the tensorial property allows you to do this. Because at any point you have something which linearly swallows in your vector at that point and then spits out the derivative which is going to lie in this section. So alternately, I can say that my covariant derivative is a map from sections to sections tensored with the dual of the tangent quadrant. So this is, you can view the covariant derivative this way. And then, maybe I'll also write this as a remark. If we have two different covariant,
sigma t in there, gamma t in there is in the place of the starting.
You mean here?
Yeah, the line above.
Here?
Yeah. I need a
Oh,
vector
yes,
field.
you're right. Okay, now this whole idea was that there's no one way of differentiating it. We can choose covariant derivatives. So what happens when we choose two different covariant derivatives? And look at the difference. So this quantity is going to be tensorial in V just because both of those are tensorial in the vector. But what about the Leibniz? What if you apply this Leibniz rule on the difference? What is your conclusion? Yeah. So the difference is tensorial. So, in particular, the difference is tensorial in its input, which means that I can do the same thing what I did here, like take this e to that sign and just say that this guy is an element of E star M tensor dual of E tensor E, which is same as this is NT. What is that? So this is, you can think of a section of NE as being a smoothly varying endomorphism on every fiber. Okay, so that's the section of this bundle. And if you want to describe the bundle itself, this is kind of an efficient way to do it, because you've taken an input in E star and output something. Or alternately, you can also think of it as a one-form value. This is a definition. So we will be encountering forms which take values not in real numbers, but which will give you values in sections. And finally, I observed that the space for any vector bundle, the space of sections is a vector space, right? In fact, it's a C infinity M vector space. So this guy is a vector space. So the difference between any two covariant derivatives lies in a certain vector space. So we have a good hold on what is the space of covariant derivatives. So the space of covariant derivatives denoted by AE is an affine space modeled on this vector space. So an affine space is like a vector space, but there is no zero on it. So it's like if you're on Rn and you take a hyperplane which is not passing through the origin. So that's an example of an affine space, where the difference between any two points would be a vector, would lie in a vector space, but the space itself is not quite a vector space because no point is zero. So there's no distinguished point which is a zero. So all these covariant derivatives are on an equal footing. So that's the space of covariant derivatives, and this observation makes it possible for us to write down these things in a concrete way, because these are just some functions which exist and you know way to work with them, but you need to write down some matrices or entries or whatever. So in order to do that, observation is quite crucial. So we'll start doing some examples. So we start with a trivial one. So remember, we took the directional derivative. That's a reasonable way of differentiating sections, right? So does that correspond to a covariant derivative? Yes, of course, because it satisfies these two conditions. So the trivial bundle comes with an obvious covariant derivative, which is the trivial covariant derivative. So I might gradually slip into calling these connections because we'll encounter them later, but I might just make a mistake now itself. So the trivial bundle has a trivial connection, which is just the directional derivative. And let me write it in a way which will be more suitable. So a section here can be thought of as a map to just Rn, because we are on a trivial bundle and we ourselves have chosen some identification between the fibers. So this is a section. So let's call this trivial covariant derivative nabla. So this is a reasonable thing to say because sigma is an n tuple of functions. So I take d component wise. So I have n one forms here and I stick in this vector field into each one of those. So I again get a function from U to R. Okay. Now we stay on the trivial bundle and then use that thing which is derived. So if you know one connection, you can get all the connections by adding an element in that vector space. So any connection, rather, any connection is of the form B plus A, where A is an element. So
We called it nabla, but you started writing D.
yes,
No, yeah.
yeah. Let me call this thing to start with. Okay, so what should I put in place of NE? Because we are on a trivial bundle, we can simplify our notation a little bit. Huh?
N cross N matrix.
Exactly. So it's just N Rn, which is n cross n matrices. So it's an n cross n matrix of my choice. Alternately, you can think of it as a one form taking values in n cross n matrices. So for example, you can say that AI dxi, where AI is AI is a function taking values in n cross n matrices, and you take n of those because, sorry, not n, there's a mistake here. Dimension of u. So let me call and x1 through xm are coordinates on u. So once I have those coordinates, I have these one forms which span t star u. So I go from I equals to 20. So we have now written down all the connections on a trivial bundle.
So on a line bundle, I can say it's the extended derivative, the directional derivative plus and one form.
Yes, yes. Because the matrix is just one entry. Right? Okay, now if someone gives you this B plus A, and sigma is a section, which means sigma is a map from V to Rn. How are you going to differentiate it? What's the expression, complete expression? So,
D sigma of V.
yes, so the D part is, we already wrote that down. We know what that is. And we need to modify it a little bit.
A of V times sigma.
Yes. So A gives out values in end Rn, so it can act on
A vector.
yeah. Vector. So this is actually a function. So that's also.
A of V times sigma. I mean, A of V is a
Oh yes.
function. It's a matrix of functions.
Okay. So A is what? Okay, so when I apply A to B, I get something. So I get an end Rn valued function, and I plug in sigma into that.
At that point.
Yeah, all this is happening pointwise. This quantity is purely tensorial. Any questions? Okay, so this is we first started out this defining covariant derivatives, saying that it will tell us how to identify nearby sections. Instead, we just gave the formula for differentiation. So now what I want to say is that now that we have this rule for differentiation, is that same as identifying nearby fibers? So that is the technical term for identifying nearby fibers is a parallel transport of a connection. So what the parallel transport is so what it does is the following. So you have a manifold and you take a path on it, and sitting above it is a vector bundle. So on the starting point of the path, you choose an element in the fiber and you want to see what are the different, if it were to stay constant with respect to this derivative we have defined, then how does it move? Okay, so that we will call gamma theta. So let me write down in symbols. So suppose we have a path and a prescribed element on the starting point fiber. So let me know. So given these two objects, parallel transport. So parallel transport is literally this lift of this path. P naught. I don't know the right words. Let me call it horizontal lift. The horizontal lift of gamma is a path, but this time landing up in the vector bundle such that gamma tilde t sits over gamma t. And it has to be horizontal, which means it's constant with respect to our connection. So when you differentiate along the path, your derivative is 0. Okay, and this is an ordinary differential equation. So when you have an ordinary differential equation, you need an initial condition, which is given by this thing. So if you think about it a little bit using the definition of connections, you'll see it does not matter that I don't have a section defined on all of M. I just have it section defined on the path. That is not an issue. That is something for you to check. But if you're seeing this for the first time, to do like a sanity check, what you need to do is see what happens in the trivial case. That's the first thing to check. So if you have a trivial bundle and you have a path on it, then what does it give you? So if you just add the opposite mark. If you have the trivial bundle and your nabla is the trivial connection, then what do you expect lifts to look like? What are horizontal lifts?
The height will be constant. With gamma not gamma tilde is given. That will be for all the points.
Exactly. Yes. So basically you think of your gamma tilde as going from a path to gamma t will be a pair. Sorry, gamma tilde t will be a pair. Gamma t, comma, let's call this sigma t, and then you differentiate. You are just doing the ordinary directional derivative because we are using a trivial connection. So we are just saying d sigma dt is 0. So your Rn component will be constant. So you just literally lift your path from the 0 section to some other thing which is constant in Rn. Okay? So sigma t is constant. So that's what you would expect the horizontal lift to be. Now, so what this parallel transport does is it gives a linear map. So basically the name parallel transport comes because you are transporting a vector in a parallel way. So as you can see in the case of the trivial connection, if you have a vector Rn, that Rn remains the same, so it remains parallel to the 0 section. So that's why this gamma tilde is, you are parallelly transporting a vector gamma tilde naught. That's what you're doing here. And alternately, you can think of it as lifting a path in the base to a path on the total space. So parallel transport gives a linear map between fibers. Which sends is that clear? So this, notice that this map is R linear. If you add two if you have two horizontal lifts, they can be added to give you another horizontal lift, and you can multiply it by a scalar, in an R real scalar, and you will get another horizontal lift. So using those things, you can show that you will mapping this starting point to the end point will indeed give you a linear map. And then since it's an ODE, the solutions are not going to intersect each other. So this is actually an isomorphism. And we are going to call this, we are going to see this more. So this is short for polynomial, which we are going to talk more about next time.
So this is the way how fibers above gamma 0 and gamma 1 are identified.
Exactly.
But this depends on choice of the path.
Yes, that's a good point. So we have found a way of identifying the fiber over gamma 0 and gamma 1, but then the next obvious question that arises is, does this depend on the path gamma? If I move the path keeping the endpoint same, am I going to get the same identification? And that's something we'll answer next time. So is dependent on path. And this is for next time. Okay, and an exercise which is something you should try is, if you know the lifts, if you have the data of all lifts available, okay, then you can write down what your connection is. So the lifts contain all the information that goes into a connection. This is a strange way to state a problem, but you will understand what I mean. If you know all lifts, you know the connection. And what I want you to do is the following. At any point, write down what you take a trivial bundle and you need to obtain a connection D plus A. So write down what A is. So if you need to write down any entry of this matrix, tell me what is the path you are taking and what is your starting point for your horizontal lift. And so if you know that what the horizontal lift is, how can you determine your A? So that's what you need to do for this exercise. Okay, so I just have 5 minutes left. Maybe I should just stop. I won't start principal point.